One convenient way to represent sets is what are called Venn diagrams, and that will enable us to clarify a couple of the things that we haven't talked about yet. So a Venn diagram, it's conceptual. You can't prove anything with it, but it can really help cement your thinking down. So what I've done here is I've given something that I'm calling a universal set, U for universal. And most sets, you're talking about numbers or something. So shoes are not part of that universe, or guitars are not part of that universe. But if you're talking about musical instruments, then the set might include guitars, or it might include bongos, or it might include all kinds of other things, but there won't be any numbers. 17 is not a musical instrument. Actually, I know a guy who's so musical that he could probably make 17 into a musical instrument, but that's weird. So there's usually a universal set that's going on. And so what we can do is we draw the universe, and then we can make some kind of shape representing a set A. You can't interpret this too literally. It's just, oh yeah, these are the things in A. Okay, fine. And then, and so one of the things that we can talk about is the complement of A. And so that's everything that's not in A. So I'm kind of shading that in. So there are a couple of standard notations, A prime, A raised to the C power. No, it's just a superscript C, or A bar. And using set notation, it's the set of X such that X is not in A. So that's the complement. So you see how the Venn diagram kind of clarifies what's going on there. Okay. Another quickie Venn diagram, let me just show you, is I'm going to stop labeling the universal set, but we could have a set A in red and a set B in green. So that's a typical kind of thing that you see with a Venn diagram. And you can have their intersection. So that's the things that are in both. So that's kind of a conceptual picture of A intersect B. And the union would shade everything that is in either one of those. There's another kind of operation that we do that isn't always done with sets, but it can be, and that's exclusive OR. So OR is like union, and exclusive OR is the set of things that there's not, after all these years, this is one of the most important set operations in computing, because it's actually the basis of binary addition, but there's no good symbol for it. Anyway, so I'm just going to write it as exclusive OR, and it's the set of things that are in A or in B, but not in both. So you get a situation like this. You get A, B. So you take the union, but then you take away the intersection. So you get a picture like this. So the purple part is the exclusive OR. Okay, there are other fancy names for it, but nobody uses those outside of textbooks. All right, so those are the situations that we might bump into, and these Venn diagrams are here to kind of help us conceptualize what's going on. Okay, so I want to propose a little bit of a puzzle, and what I want to do is I'm going to take three sets, which I'm maybe being stupid and not color coding, and I've got these three sets A, B, and C. I haven't even drawn the universal set, and you see there are a bunch of regions here. Here's a region, here's a region. And we have a simple way to encode these regions. Each of these regions corresponds to a subset of some kind. And so, and this is the computing perspective. So this is how we compute with these things. In a pure math course, you say, well, yes, there are these regions and we can label them all. But we're going to label them with numbers. And so we're going to be doing what in some languages is called a typecast. But this is the computing point of view. So I'm going to say that I'm going to make 3 columns here, A, B, and C. This is maybe someplace where you can see them. And we have this situation where some things are only in A, and some things are in A, but they're also, they're in A intersect B. That's this little kind of crescent shape. But then there are things like here that are in all 3. And so how are we going to be systematic about doing all this? And what we're going to do is be systematic by using binary numbers, by using bits. And so 1 is in, 0 is out. Seems good to me. So what we have here is our first number that we're going to use is 0, 0, 0. So something in that region is not in any of these sets A, B, and C, which means it's somewhere in the complement of their union. So that's the first thing we get. We have the possibilities of the things that are only in one set. So we have 1, 0, 0, 0, 1, 0, and 0, 0, 1. So those look like binary numbers, but these are the things that are in A, but not in B or not in C. So I'm going to label that 100 corresponds to the decimal number 4. We're going to talk about that next, how to make that conversion. I'm pretty sure you've seen that, but it's kind of good to get us thinking in the right way. So I'm going to say that that's 4. The first one was 0, and then we have 2, and then we have 1. So those would be the decimal equivalent of 4 is 100, decimal equivalent of 2 is 100, so forth and so on. And I'm going to label the regions with no boundaries or anything. So this is area 4, and this is area 2, and this is area 1. Now, if you get a big enough intersection, you can get to area 51, but that's restricted. Anyway, so region 2 corresponds, let me just kind of color that in just to make sure that we are aware of what region 2 is. And so those are things that are in B, but not in any of the others. Okay, so that's great. So we've got the things that are in one set. What about the things that are in 2 sets? So that's going to have 2 bits. The 2 bits for the sets that it's in, but not all 3. So actually, let's jump ahead and do all 3. Let's do 1, 1, 1. That's the binary equivalent of the number 7. And those are the things that are in all 3 sets. So that's this tiniest region right here. And so I'll color that. Well, I'll just call it 7. And we'll kind of indicate what region 7 is. There we go. And then the things that are in 2 sets, well, one man's meat is another man's poison, or one woman's meat is another man's poison, or one man's soy is another woman's quinoa or something, I don't know. But if you have 3 bits and 2 are on, that's like having 1 is off. So we're going to have 0, 1, 1, 1, 0, 1, and 0, oh, I'm sorry, my mistake, 1, 1, 0. So what I've done here is systematically placed the 0 bits. And so there they are in order, tic-tac-toe winner. Anyway, so, and those correspond to the decimal numbers 3, 5, and 6. And I will now fill in the regions where that is. So region 3 is stuff that is in B and C, but not in A. And so I look at the intersection of B and C, so that's going to give me region 3 like this. Remember, I'm going to scan this so you can study it at your leisure. And then, and let's see, region 5 is stuff that is in A and C, that's here, and region 6 is the only leftover region. So those are the ways that we can systematically specify the regions that are that are defined by these 3 sets. And the thing to notice here and when we talk about power sets, this will be important, is we've got 3 sets that are working here, and there are 8, which is 2 to the 3 power. And that's easy to see because we've got the different ways of filling in these bits. Everything is either in or out. So there are 2 choices for A, 2 choices for B, 2 choices for C. 2 times 2 times 2 is 2 to the 3rd power, which is 8. And so that will show this relationship between powers of 2 and subsets. And that's what's going on here. So this way of doing things, this gives us a lot of tools that we can use. These are kind of, if you've studied C or C++, these are typecasting tools. We're taking things that are Booleans, basically. That's not something we haven't defined, but it's something that we're talking about. You know, A and B or C, or A or C or B, or so forth and so on. You know, we got 3 truth values, and we can convert those into numbers. And then we can treat them as integers and do all kinds of other stuff with them, which is fun and useful. So Venn diagrams, thinking about things in the computational way, complicated pictures. This picture will come up again, and that's a really fundamental to everything that we're going to do in the rest of our lives.